chair of the evening program. I also teach in the department, and I'm the person who's responsible for the Capstone experience. Through the whole thing, so the last team isn't presenting to me. It's very discouraging. So hopefully we'll get out a little bit early and get home in time to watch the end of the Seahawks. The Mariners lose. I hear they're bringing Rodney in for a command performance. So, the first talk is sponsored by PACCAR, and of note is that one of the engineers at PACCAR who mentored this team is Frank Chu, who was one of our students. And so we're now beginning to see that our students going out into industry, becoming experienced engineers, and then giving it back by mentoring teams coming out. So, the title of the talk is Adjustable Roof Fairing for Tractor Cabs. The team members are Josh Custer, Amy Johnson, Kevin Jorgensen, and Wayne Kimura. Here is their faculty advisor. You're up.
Thank you, Dr. Carter. So like you said, this is our project on adjustable roof fairing for tractor cabs, and Kevin Jorgensen is a team leader. And again, our Capstone faculty advisor is Dr. Wayne Kimura. Our industrial advisors were Mike Repko and Frank Chu, and our sponsor was PACCAR. So today I'm going to be taking you through the introduction and the background motivation behind our project, as well as continuing on to the approach to our design and the description of the design. Finally, going through the results, the reflections, and some advice for future Capstone teams. So who's PACCAR? PACCAR started in 1905 in Seattle, Washington, and now the headquarters resides in Bellevue. PACCAR pretty much designs and manufactures anything related to light, medium, and heavy-duty trucks. They also have merged and owned companies such as Kenworth, Peterbilt, and in Europe, Dodge. So for some motivation in the background behind this project, in 2014, DOT and EPA set up some new fuel efficiency standards to reduce fuel consumption by 20% by the target year of 2018. So a good way to do this was to increase the aerodynamics of the truck. So this is why a lot of the newer trucks are a lot more rounded versus the old square bodies that we're used to. So hence why they came up with the proposed project for an automatic adjusting roof fairing on top of a tractor cab. So what is a fairing? It's an external metal or plastic structure added to the top of semi-trucks to increase the streamlining effect and reduce the drag of the vehicle. So some of the trucks, such as this one, have an integrated roof fairing, which saves about 15% efficiency. This here is a one-dimensional manual adjusting roof fairing, and this truck here has no roof fairing. So today, as of today, there are no automatic adjusting roof fairings. So it's just the integrated and the manual adjustable roof fairing. So now I'd like to pass it on to Kevin Jorgensen to go over our target goals.
Thank you, Josh. So, as we began to research this project, we knew that we needed to be able to bring the fairing from parallel with the cab up to the height of the trailer, and then adjust varying on the wind speed and wind direction. The fairing also needed to be able to operate at up to 210 miles per hour wind speeds. It needed to operate in all weather conditions and in all harsh climates. There needed to be minimal driver interaction, that way the driver would not get distracted while he was driving down the road. On top of that, it needed to automatically adjust while the truck is moving. So as the truck is going, it needed to be synchronous with time, that way that it is always accurate. And it needs to be able to detect if there is no trailer attached. This way it does not prop straight up with wind coming on, causing more air drag. As we first looked into the project, we divided it into two topics. There's a hardware design and a software design. The first thing we looked at is we knew that we needed some way to adjust the fairing going up and down. For this, we chose an actuator, where an actuator is a motor that moves some sort of system or mechanical design. In order to get the trailer height and the wind conditions, we needed some sort of sensors. And then to integrate all the sensors together, we would need a microprocessor. And since a microprocessor is a mini computer on a microchip, this means that we're going to have software design. The first thing we looked at with software design is the communication. And if you look at our Tier 1 diagram, you can see the actuator, the trailer height sensor, and the wind sensor all have these communication buses that go straight to the microprocessor. Once they go to the microprocessor, all that data is then looked at, and then is sent, the fairing algorithm is then sent back to the actuator to adjust the actuator where the fairing needs to adjust to. Once we get this all figured out, we knew we wanted some sort of error protection. So that way, if one part of the system goes faulty, there's not more catastrophic damage caused to the system. When we first looked at the actuator, we knew that we needed to adjust the fairing angle using some sort of electric actuator going off the truck's battery. It needs to also be able to communicate with the microprocessor, telling the microprocessor the current length of the actuator, as well as being able to be controlled by the microprocessor. On top of that, there's the automotive standards that were provided to us. This means that this whole system had to be durable and robust, it had to be able to withstand extreme temperatures, and it also had to be able to deal with harsh climates. On top of that, it also had to deal with the corrosion that is caused from salts, corrosive materials thrown down on the roads. And it also needs to be compact enough to fit on the roof of the cab and get onto the fairing. As we began to look into the wind sensor, we knew that the wind sensor needed to be able to measure the oncoming airflow, meaning it needs to be able to measure both the wind speed and the wind direction coming across it. It needs to be able to provide this data for adjusting the fairing angle, so that it can be sent to the microprocessor. On top of all this, it needs to be able to abide by the automotive standards as well, and it needs to be small enough so that it would not impede the airflow caused by the wind. The height sensor needed to be able to determine the initial fairing angle upon startup, and it would do this as the fairing would move. The sensor would be able to detect the height of the trailer. So every time the fairing moved, the trailer height would be detected. For this to happen, it needed to be able to read at distances up to 6 meters to determine the height of the trailer. And it would also need to be able to function elements including direct sunlight, so that the sunlight beams would not interfere with the laser's receptacle. As we looked at the microprocessor, we knew that the microprocessor needed to process the information from the sensors and the actuator, meaning we wanted to design a system or use a microprocessor that had at least 3 serial communication ports. On top of that, we also wanted an analog and a few digital pins in case we would need those for any other designs that would come up later in the project. As we began to look at the software, we knew we needed to first integrate all the communication between the components. We'd also need to come up with algorithms to adjust the fairing height depending on the wind conditions and the trailer height. And we needed to be able to calibrate the system based on multiple tractor and trailer combinations. And then on top of that, we needed to check the actuator and the sensors for errors. So what we came up with in our top level diagram, as we started with the startup, we would then get the trailer height, and once we have the trailer height, we move on to read data from the wind sensor, and then with this data, we put it into an algorithm that allows us to calculate a new position for the fairing. And once we have calculated this position, we would then adjust the fairing accordingly. Now I'll now pass this on to Amy Johnson, who will talk about the description of our project.
Thank you, Kevin. The photo above shows the original fairing. We needed to replace this metal support bar with an actuator to move the fairing up and down. We chose the Servo City linear actuator, shown here, which is able to communicate with the microprocessor, as well as lift over 3,000 pounds. This is enough to lift the fairing, as well as make up for any wind pressure coming towards the fairing. The actuator uses a set of relays, which switch the voltage polarity to move the fairing up and down. We chose a photoelectric sensor to be placed at the top edge of the fairing to detect the trailer behind it. The sensor sends out a light beam which is reflected back from a reflector placed at the top of the trailer. This reflection indicates that the top of the fairing is level with the top of the trailer, and the actuator will stop moving the fairing up. We chose an ultrasonic wind sensor to detect oncoming wind conditions. The ultrasonic wind sensor uses acoustic resonance to measure the airflow coming towards the fairing. This model is lightweight, compact, and rugged enough to be mounted on top of the cab and in front of the fairing. When the air that flows through these gaps is measured at 5 measurements per second, this information is then sent back to a microprocessor. We chose the Arduino Mega 2560, shown here, as our microprocessor. The Arduino is capable of receiving the high-low voltages from the height sensor, receive data from the actuator based on the length of the piston, and receive data from the wind sensor based on wind conditions. All this information can then be processed to calculate and communicate a new fairing position back to the actuator. We designed a printed circuit board to connect the Arduino to the connections to the sensors, actuator, relays, and liquid crystal display. The PCB also included a power rail and all of the necessary resistors, capacitors, and diodes needed for circuit functionality. The Arduino runs a C++ software used to integrate communication between devices. When the vehicle is turned on, the software will check for any errors in the components, such as a broken sensor. If an error were to occur, an interrupt message would then be displayed on the LCD. If there is no error, the software then instructs the actuator to move up until the fairing is level with the top of the trailer. Once the fairing and trailer are aligned, the Arduino will take wind data from the wind sensor to calculate the optimum angle for streamline effect. All this information is then sent back to the actuator to change the fairing. Our results. We put our fairing display on a piece of plywood to simulate the top of the cab. Our actuator was able to fit nicely underneath the fairing as well as lift the fairing, and it was able to communicate well with the Arduino. Our height sensor mounted here got reflections back from this reflector mounted on a stand to simulate a trailer. This was also able to communicate well with the microprocessor. Our wind sensor, shown here, used an LTC485 chip to interpret the serial data between the Arduino and the wind sensor. To test our wind sensor, we used a box fan to simulate low wind speeds. This box fan had 3 different settings, which we used to move the fairing to 3 different positions. Our user interface included an LCD and 3 buttons. Our LCD was able to read the trailer height, the fairing height, as well as any errors should they occur. Our PCB is still in the process of being manufactured. I will now give it back to Josh Lester.
So as you can see, there are quite a few future development ideas for this project. One being is to improve the fluid movement of the actuator, as right now it moves quite quickly and it's a little jumpy, so it'd be nice to make that more fluid. Also, installing the fairing system onto the tractor cab for future testing via the track or the wind tunnel to come up with a more accurate algorithm based off the wind speed and the integration of wind direction, as we were only able to simulate this with like a box fan and low wind speed data. Also, it'd be nice to include this our system communication with the truck's computer. That way, they can pull off other conditions such as the steering wheel angle, the tire pressure, etc., to also make that algorithm more accurate for a more efficient system. Lastly, we would like to add a calibration system and account for more tractor and trailer combinations. So looking back on our reflections on this project, there were multiple keys to success. One thing is that we were able to assure that all of our components were integrated and tested correctly, and our research really paid off. Also, we started presentation and project reports early while waiting for parts, and we also set regular team meeting times and work times and stuck to them, and it worked very well for this project. Also, we did not get to procrastinate as we didn't have any time to. As far as advice to future Capstone teams, understand that your industrial advisor is extremely busy, so try to be flexible with their time. If you can, try to maintain some sort of communication or meeting times with them throughout your quarter. Last, don't be afraid to go to the UW professors or other students early when you're having challenges, because this can really help overcome those obstacles. So, all in all, for the final summary here, is our system is able to find the trailer height upon ignition, detect wind speeds when mobile, and adjust the fairing accordingly. All in all, this will help with better fuel efficiency. So we'd like to acknowledge and thank the following: PACCAR for being our generous industrial sponsor, Mike Repko for being our industrial advisor, Brent Chu for being our assistant industrial advisor, Dr. Wayne Camara for being our Capstone advisor. Without his skills and time efficiency and organization, we wouldn't be able to finish this project on time. Dr. Arnie Berger, who established this project, also helped us overcome some challenges with the wind sensor itself, as well as go over our PCB design before we ordered it. Enoch Fu for software help. Dr. Pierre Murad and Ida Bowen for giving us our luxurious private room here in Discovery Hall. And last, Larry Burris for filming currently, and he also is a great resource to go to for any students as far as if you're looking for anybody on campus or any other resources. And this now concludes our presentation.
Any questions?
Your wind sensor, what do you expect you would do in conditions of snow? Just tell the driver to brush the snow off, or would you think you'd heat it or something like that?
Gotcha. Glad you asked. So the wind sensor actually has a lot more capabilities besides the wind speed and direction. It also is incorporated with a compass as well as a self-heated system. So you can actually set the temperature, minimum temperature range, so if the temperatures drop below that, it'll actually keep on the heater until the device is at that temperature.
And so you can melt the snow, right?
Exactly, yep.
What does a wind sensor like that cost?
You know, I don't know if we're able to disclose that information.
In comparison to an integrated roof fairing, how efficient is the self-adjustable roof fairing?
That's something we really haven't gotten to have tested yet.
This is the proof of concept, so we have not been able to put it on a truck yet. And since there are no other automatic fairings on the market, we don't know. That will be later in the wind tunnel testing.
Any questions? Actually, Brad?
So are any of you going to continue like a relationship with PACCAR to follow this through is PACCAR going to continue to use the research and work you've done?
Yeah, they do seem like they're going to continue on this project. They didn't give us a timeline, so we don't know when it will fit in, since they do have a lot of projects.
Okay.
But we would be interested in seeing where the project turns up. That's something we're interested in.
Okay.
We have one of our good friends who was our assistant industrial advisor as well, so we will stay in contact with them. And one thing we did get to present to our industrial sponsor a couple days ago, and they did say that they're targeting this product to be in the field by 2018.
Wow.
Maybe you could moonlight, at night.